Today we're going to talk about the laws of thermodynamics, and thermodynamics is a could be taught as a whole course in its own right. So we're going to condense a lot of material into a short amount of time. So there are three laws of thermodynamics. And there's actually a fourth law that we call the zeroth law. And we've already talked about what the zeroth law is, and that's that there's this thing called temperature that an object has, and temperature is a measure of the average kinetic energy of the particles in an object or material. And we last time we talked about heat transfer, and the first law of thermodynamics will be related to heat transfer. And it's really just a restatement of the conservation of energy. So the change in energy for a system, and this will be the internal energy, is the heat transfer plus work. So this is heat transfer. This is work. And with this heat transfer and work, the sign of the heat transfer and work will kind of depend on the way a question is worded. So the heat transfer into a system is positive, and then the work done to a system is also positive. But the work, or sorry, the heat transfer out of a system is negative, and the work done by a system is negative. So depending how a question is worded, heat transfer can be positive or negative, and work can be positive or negative. The second law of thermodynamics states that it's impossible for any heat transfer system to convert all energy into work. And we'll talk about the implications of all these laws in a moment. And then the third law of thermodynamics, the vocabulary word term for it is entropy. And the definition of entropy is that the disorderedness increases universally. So what that means is that you can have a system that you make more ordered, but in order to make that system ordered, you had to increase the overall entropy or disorderedness of the universe. So, for example, if you have a very messy room and you clean that room, your room has now become ordered, but you haven't broken the third law of thermodynamics, because how did you bring order to that room? You had to put in a lot of work and energy in order to clean up your room. And all of that work and energy created heat, and that heat escaped into the environment and the universe. So even though the disorderedness of your room decreased, the disorderedness of the universe increased overall. And kind of a secondary to this idea of entropy is that entropy approaches a finite value as temperature approaches absolute zero. So if you were to make a graph of your entropy versus temperature, as your temperature decreases, your entropy might stop at some positive value, even though your temperature continued to decrease to zero. Okay, so let's see some of the applications and implications of thermodynamics, and that is with the heat engine. So let's say I have a room full of hot air. So this will be my hot room. And then I connect it to a ventilation system and connect that to a room full of cooler air. So I'll call this the cold room. Now, when I open up the vent from the hot room to the cold room, I will get heat transfer between the hot room and the cold room, and eventually the temperature of the rooms will reach an equilibrium point. So, how do I extract work from this system? Well, what if I put a little fan in the middle of my duct connecting the hot and the cold room? When air rushes over the fan will start to spin, and maybe I connect that fan to some rope and connect a mass to the bottom of that rope. So now I open the vents between the hot and the cold room. The air flows from hot to cold. The flow of air causes this fan to spin, and as this fan spins, the length of this rope will get shorter, and thus the mass will be lifted. We saw previously in the semester that when you lift a mass, you're doing work, or you're uh, giving that mass some potential energy. And so at maximum efficiency, the change in energy should be zero. And so I'm basically converting all of this heat transfer into work by raising this mass. And so the work done by this system on that mass that we're trying to raise should be the heat transfer from the hot room to the cold room. So this is a very basic example of how a heat engine might work. What you might notice, however, is that the second law of thermodynamics says that we can never be operating a heat engine at maximum efficiency. So the second law of thermodynamics states that we can't operate heat engine at max capacity or max efficiency so let's define the efficiency of our engine to be the amount of work that we can do divided by the heat transfer from the hot side of the room. So on the previously we defined the work done as the heat transfer from hot to cold, and now we're dividing that by the heat transfer from the hot room. So we can simplify this to be 1 minus QC over QH. There's a certain type of heat engine called the Carnot engine. And for a Carnot engine, the heat transfer is just related 1-to-1 to the temperature of the cold and the hot. And so our efficiency becomes 1 minus cold temperature divided by hot temperature, or hot temperature minus cold temperature divided by hot temperature. And so let's do a calculation maybe for this example room and the two hot and cold rooms that we were using earlier. So let's go back to our very simple picture. And let's say the temperature of the hot side of the room is, let's say, 100 degrees Celsius, and the temperature for the cold side of the room is 0 degrees Celsius. If we naively tried to calculate our efficiency using the Celsius temperatures, we would get 1 minus T cold over T hot, and that would be 1 minus 0 over 100, and that would equal 100% efficiency. And we know that violates the second law of thermodynamics. But temperature could even be negative. We could have negative 5 degrees Celsius. And so that would give us an efficiency actually greater than 100%. 1 minus negative 5 over 100. So 5 over 100 would be 0.05. And so this would be 100.05% efficiency. This would be 105% efficiency. So clearly, this is not correct. And instead, what we need to do is calculate our temperatures using So this is obviously not correct, and instead what we need to do is calculate our temperatures in Kelvin. So 0 degrees Celsius will be 273.15 Kelvin, and 100 degrees Celsius will be 273.15 plus 100, so 375, or 373.15 Kelvin. Now if we calculate our efficiency, we get 1 minus 273.15 over 373.15. And so our efficiency would be 0.268, I'll call that, or 26.8% efficiency. So not a very efficient engine, but this was just a kind of toy example that we came up with. Another application for that uses these laws of thermodynamics is a heat pump. And so you can think of a heat pump as a heat engine working in reverse. And so examples of this are the refrigerator in your house that keeps all of your food cold, the air conditioning system that keeps your inside temperature colder than the outside temperature in the summer. And so there you're doing work on a system to remove the excess heat, basically. And so the equation that we're going to use to describe a heat pump, so this COP term is the coefficient of performance and this equals the hot side of your heat transfer divided by the work, or 1 over the efficiency, which would be the hot temperature minus, or hot temperature divided by the hot temperature minus the cold temperature. So because a heat pump is just a heat engine working in reverse, we could take the efficiency if it was a heat engine and then just do the reciprocal of that. And so let's calculate the coefficient of performance for maybe a refrigerator. So the refrigerator needs to keep things just above freezing, so let's say that's 1 degree Celsius. And let's say the underside of your refrigerator is fairly warm, and so a bit above room temperature. Let's say 320 Kelvin. So again, let's make sure everything is in units of Kelvin before we start. So this 1 degree Celsius would be 274 Kelvin. So the coefficient of performance for this heat pump will be 320 divided by 320 minus 274. And when you plug that into your calculator, you would get a coefficient of performance of, let's round that to about 7. And so depending on your surrounding temperature or the temperature that you want to reach with your heat pump, this coefficient of performance can vary. And just like your efficiency for a heat engine can never be greater than 1, your coefficient of performance shouldn't be less than 1 for a heat pump.